So thank you very much. Thank you for inviting me here. It's great to be here. So my name is Antonio Lieto. I'm an assistant professor at the University of Turin, Department of Computer Science, and a research associate at the National Research Council in Palermo in Italy. So I will give two talks in this school. And so this is the first part of the story, let's say. And as the title suggests, I will talk about common sense reasoning and some application of a framework which is called TCL that I've been working on with my colleagues in the last couple of years. So the main focus of today will be around this notion of common sense reasoning. Michael has already sketched some of the implications and why it is important to enable, let's say, cognitive system and cognitive robotic system of this kind of capability, which is pervasive in human cognition. So, why it is important to, let's say, stress this issue? Because there is this famous book, and I think this is, let's say, mainly probably the main inspiration of people working on common sense knowledge and common sense reasoning. This famous book by Marvin Minsky, where he provided, let's say, the idea that common sense knowledge can be really, let's say, the elements that connects perception and higher level cognition. So this is probably, let's say, one of the most important gateway that allows us to, let's say, actually do what Michael was showing in the previous lecture. And of course, when we talk about common sense knowledge, we also have to deal with the reasoning capabilities which are enabled by this kind of common sense knowledge. This is not, let's say, a new theme in the context of AI. Here you can see, let's say, a very partial overview of some of the frameworks or of the formalism that have been developed so far, let's say, within both the area of more cognitively inspired system, but also in the area of more, let's say, machine-oriented approaches to solve the issue of common sense reasoning. So this is just a partial overview that, let's say, gives you the idea of the importance of this topic. But what is common sense reasoning? So what are we talking about, right? So let's say what we can say in an informal way is that common sense reasoning concerns, so have to deal with all the type of non-deductive or non-monotonic inferences, like induction, abduction, default reasoning, and so on and so forth. The problem, however, is that having this kind of logic-based, let's say, taxonomy is not enough, because another important ingredient of common sense reasoning is the notion of typicality. So not all the kind of inductive inferences have to deal with the typicality. So not all the inductive inferences are, for example, can be ascribed to the category of common sense reasoning. This is a notion that comes from the cognitive psychology. This is a very famous work by Eleanor Roche that started this tradition. So let's try to have a very simple example. A kind of common sense inferences that we do very quickly, very easily, is, let's say, a type of non-monotonic categorization like this one. Like if I tell you that you have to categorize this X and you have this, let's say, cues, so you know that X barks, has fur, I don't know, woof, and something like that, probably the answer that immediately comes to your mind is, okay, well, X is a dog, okay? Note that this is a type of non-monotonic categorization, because all these cues are neither necessary nor sufficient for identifying something as actually a dog, okay? But we perform this kind of reasoning, say every day, okay, multiple times a day. So this is a very powerful form of inferences that we are able to make. What happens, for example, in the field of knowledge engineering, or at least in part of the field of knowledge engineering that nowadays mainly deal with the problem of knowledge representation? Let's consider, for example, ontologies or, let's say, knowledge graphs, okay? Because today there is this rebranding of ontology, and so they are nowadays called knowledge graph. What you can do in standard ontologies knowledge graph is to have this kind of definition of the concepts that you represent. For example, you can say, look, that a triangle is something that is a polygon with 3 corners and 3 sides, okay? But the problem here is that this kind of structure, so this kind of symbolic system, the way in which they are designed, are only able to define this kind of, let's say, this kind of very fixed concepts. So these are called usually classical concepts. So these are concepts where you have necessary and sufficient conditions for the definition of this concept. Of course, let's say, behind this kind of representation that you can do with ontologies on knowledge graph, there is the reasoning part. So you can infer that every instance, every data point that has these properties then can be classified in a deductive way, okay, in a deductive way as a triangle. What is the problem here? So here the problem is that common sense concepts, okay, like chair, like game, like all the type of concept that we have to deal in our everyday life, cannot be defined in this precise way, okay? So we have definition only for very particular type of concept, like, I don't know, mathematical concept and so on and so forth, okay? But common sense concept cannot be defined in this way. And this is a problem because, let's say, the standard formalism that are used in ontologies and in knowledge graph, which are the description logics, okay, only allow the possibility of having this kind of classical definition. And therefore, they are only able to have forms of, let's say, automatic deduction. Okay, like in this case, like exactly in the case of the triangle. Of course, I mean, it is possible then to add a little bit of non-monotonicity by using external rules and whatever. But let's say the standard formalism that are used in ontologies allow to have this kind of very standard, let's say, types of deduction, which is not what we need, okay, in order to do all the things that we want to do. And in particular, let's say, this notion of concept, which is implied by the semantics used in classical description logics and therefore in ontologies, does not allow to represent and reason on typicality, which is, as I mentioned, a very important ingredient of common sense knowledge. So what happens is that usually in practical application there are many ad hoc solutions that have been adopted. Like, for example, the idea is that it is possible, even if the semantics underlying the ontologies and knowledge graph only allow to have that kind of classical deductive representation and the deductive reasoning, the idea is that it is possible to use ontologies as a sort of frame structure a la Minsky, where you have actually slot values schemas, and in this structure it is possible to for example, represent this kind of information, like the birds fly, okay, by assuming that this kind of class has represent the typical birds. Okay, so you can have in the ontology, you often have this kind, this type of representation, assuming a common sense representation of this concept. But actually, the concept is not represented in a typical way. So this inclusion here means that there is no exception to the fact that birds fly, okay? So in this case, for example, it will be difficult to include penguins in the category of birds. So there is no way to deal with this aspect. So using this kind of structure, this kind of representation in a common sense way, in a, let's say, frame, in a sort of frame structure, Alaminsky doesn't work, okay? Because the semantics underlying this kind of representation doesn't allow you to tell that typically birds fly. And actually, it is also not possible to do the experiments that we have done before. So you have to add external, let's say, ad hoc rules to deal with this kind of, for example, non-monotonic categorization. Now, one could say, well, okay, but in specific applications, I can use ontologies and this kind of symbolic structures in a way that resemble the use of frames Alaminsky. So I can, let's say, intend the meaning of that kind of representation in a, with a typicality-based semantics. But there are some problems here. So from a knowledge engineering perspective, we can just build very narrow applications that don't communicate with other, let's say, knowledge bases, okay? Why? Because it is not possible to generalize this kind of, let's say, typicality-based assumption on non-typicality-based semantics. So this is an important problem, and the problem explodes if we want to integrate, for example, shared ontologies, shared knowledge bases with other people. So why this is problematic? It is problematic because actually prototypes, so typical representation of a concept, and common sense knowledge are dynamic and are context dependent. Okay? So what does this mean? It means that, for example, while in certain parts of the world, but I assume also here, a robin can be a typical representation of for the category of birds, okay? So we can ascribe to the prototypes the typical representation of a bird, all the properties of a robin. In other parts of the world, well, this is a typical bird, okay? A kiwi. Like if you are in New Zealand, this is your prototype, okay, of birds. And kiwi, for example, don't fly, okay? Or have different dimensions from the prototypical bird. So if you try to integrate, let's say, two ontologies, okay, assuming a non-typicality, let's say, semantics on, assuming a typicality-based semantics on, let's say, ontology, which don't support typicality-based semantics, you just have an inconsistency here. Because you have, let's say, conflicting requirements attributed to the same class of birds. So that's why doesn't work the kind of approach that is often used also in the field of cognitive robotics. And it is possible to do a bunch of other examples, but this is the same example done, for example, for the apple. This may be the prototype of apple, for example, for some parts of Italy, while for the south, while, for example, in the north of Italy, these are the typical apples, and so on and so forth. Okay, so it is full of problems like that. Prototypes are dynamically built and are always context dependent. So this means that we need a way to handle this kind of inconsistencies, and we need a way to handle exceptions to inheritance. Okay, so this is an important, let's say, piece of the things that we will see in this couple of lectures. Okay, so the notion of typicality and how it is possible to handle typicality. Okay, another, let's say, ingredient of let's say my presentation concerns the notion which connect common sense reasoning and compositionality, which is another, let's say, very important issue. It was mentioned also by Michael before. Now, compositionality is a very important trait of human cognition. It is a very important generative requirement, which is assumed in biological cognitive systems. We can, let's say, define compositionality in this way by using this Frege's principle, okay? By saying that for compositionality, we mean that we have this kind of modular, let's say, the possibility of having modular composition and decomposition of constituents, okay, in order to understand what is the meaning of a function. And this is an example coming from natural language processing. If I say the cat is on the mat, it means that all the constituents of this sentence can be, let's say, be understood by based on the relationship that they have with the preposition on. But if I say the mat is on the cat, I specify a different meaning, okay? The way in which the same words are used to compose the meaning is completely different. Now, by the way, compositionality is something that comes, let's say, for free in a symbolic system. Okay, it is a crucial component of, in general, the physical symbol system hypothesis. But nowadays, it has been also argued that systems like GPT-3, since they are able to have these forms of, to make these forms of text completion task, okay, are able to deal with the notion of compositionality. Now here, this is a, let's say, very famous example by OpenAI, where you have the prompt that is given here, and this is, let's say, the text that has been completed by the system. It has been argued that since the system is able to complete in a, let's say, an understandable way, okay, this kind of narrative, then the system is able to handle with compositionality. This is not true because, well, text completion is a prediction text. It's not a text of compositionality. So pay attention to, let's say, this kind of claim, okay? And another thing that is problematic for this kind of system, in general for the transformers, okay, is that there is really lack of common sense reasoning. This is an example that I've taken from Davis and Marcus, where the prompt given to GPT-3 is something like this. So you are having a small dinner party, you want to serve dinner in the living room. The dining room table is wider than the doorway, so to get into the living room, you will have to. This is in bold, you see the answer provided by the system. And the system says, oh, you have to remove the door, or you have to, let's say, split the table in two, something like this, okay? So these are, let's say, example of lack of common sense reasoning. And for what concerns the lack of compositionality, well, this is another example that I made on GPT-3. This is a typical case, let's say, typical sentence that you used in, let's say, the first courses on natural language processing and so on. So if we give this prompt to GPT-3, like the trophy doesn't fit into the brown suitcase because it is too small, and then you try to ask what it is too small, well, the answer of the system is the trophy is too small. This is a problem of compositionality because the system is not able to actually deal with the problem of anaphora resolution, right? So it does split the constituents of that compose the meaning of the sentence in a proper way. And one could say, okay, but what if we move out from GPT-3 and consider, for example, DALL-E, which is this other, let's say, great system that is used to generate images from text that is given in input. Well, you see that it has exactly the same problem. Because, for example, for a prompt like this one, a red cube on top of a blue cube, these are the type of images which are generated. okay? So we are not talking about complex sentences here, okay? We are talking about this kind of prompt. So this show how all these systems, actually transformers have a problem with dealing with this kind of compositional structure. And on the right, you see also that there are, this is a caption that says, a red basketball, I want to get you draw a red basketball with flowers on it in front of a blue one with a similar pattern. So this is a little bit more complicated with respect to this one, but still, this is the type of, let's say, images that are generated, okay? So one question would be, are these systems just, let's say, good at memorizing and storing a large amount of information and then try a way to, let's say, recombine it in order to present a plausible output? This is an open question. So, but we know that there are problems with this kind of system dealing with compositionality. This is another example. So a horse that rides an astronaut. You see that here what we do, actually there is no way of having a correct, let's say, division in constituents in the task of semantic pattern. So this is the result of this kind of prompt, okay? So they are just reversed because, of course, probably the system assumes in its memory that usually the horses are more frequently, is more frequent that a horse, let's say, has this role with respect to, let's say, someone that rides it. Again, still on DALL-E, and still another example, this system is not able, again, to deal with the negation, of course, okay? There is no giraffe standing next to the man, okay? And these are the kind of images which are generated. So we are talking about very basic kind of sentences. There is no, let's say, complex NLP pipeline involved here. But this is to give you, let's say, an idea of how it is difficult for this system. And this is a foundational problem. There is already, let's say, a work by Fodor and Filichin in 1988 that shows how, in general, neural network systems have problems in dealing with the problem of compositionality. So despite all the progresses that we have done, these problems are just, let's say, were just left hidden under the carpet, okay? So they are still there. Or this is another, let's say, fancy example of a system that use the same kind of transformers that provides captions for the images, okay? And here, for example, you see that in this case, the caption that is provided is a woman riding a horse on a dirt road. Or here, a group of people standing on the top of a beach, okay? So, it's dramatically funny, right? But okay, so this is just to give you an idea of the notion of compositionality I wanted to talk about. But this compositionality mainly deals with, let's say, a natural language processing pipeline. What I would like to talk about today and in the next lecture is about these other forms of conceptual compositionality. So how we compose a typical representation of a concept, so prototypes of a concept, in order to generate novel knowledge, novel concepts, okay? Now, this is an important issue because, as I said, while compositionality is something that comes for free from symbolic system, common sense compositionality is problematic. It is problematic because we encounter this problem which is called the pet fish problem or the Guppy effect problem. So the problem goes as follows. Imagine that we have a typical representation of what is a fish. Okay, so we are these features of a typical fish. And then we have these features of a typical pet. okay? And then we want to compose the concept of pet fish. Well, what we see actually is that this concept is not composed by the additive inclusion of the typical features of the two concepts, like, right? So we have, for example, that a pet fish lives in the water, which is something that inherits from here. It is not warm, that still inherits from here. It is red, which is a property that is added and then was not originally available in either two of these concepts. So how this kind of common sense conceptual combination works and why it is important. It is important because this is the way in which we generate new knowledge. So we deal with the common sense representation of the concept, and one of the most powerful generative way that we have in order to create a new concept is by using this kind of common sense compositionality. So solving the pet fish problem means to, let's say, have access to the kind of abilities that we have in order to generate new knowledge, to generate new concepts, okay, in a more creative or in a less creative way. So this is actually the focus of this framework that I've developed with my colleagues Gianluca Pozzato and Daniele Perrone at the University of Turin. This is a logic framework which tries to apply to solve, let's say, this pet fish problem in the context of ontologies and in the context of standard knowledge graph. So it is a framework that is based on 3 ingredients. And first of all, it is a non-monotonic description logic of typicality. So it extends standard description logic formalism in order to represent typical information and in order to reason on typical information. Because typicality is another important part of, important ingredient that we need in order to have this kind of common sense conceptual combination. This first, let's say, logic is enriched with probabilities and with distributed semantics coming from logic programming, which is called Disponte semantics. I mean, I will not show you here all the syntax and semantics. This is, let's say, the reference paper. But I want to give you the idea of how these pieces go together within the formalism. And finally, I will show how we use an heuristic coming from cognitive semantics, which is the so-called head and modifier heuristics, that allows us to deal with the problem of the pet fish. So this entire formalism has been designed to deal with the problem of the pet fish, so compositionality of typical representation that I've showed you before. So let's see a little bit what we have here, right? So the first thing that we have is, let's say, the combination of, let's say, a logic of typicality with distributed semantics. Okay, let me see. Okay, so if we see the logic of typicality, what we can say is that we have extended the possibility in ontologies and in description logics to let's say, express assertions like this one. So we can say now that there is a typical C that is also a D. So we can say that, for example, that there is the typical students are usually Facebook users. Okay, there is this typicality operator here that has been introduced. And this logic allows us to deal with, let's say, inconsistency, like, or with exceptions to inheritance. Like, if we have this example here, this knowledge base here, so we know that there is a typical wrestler which is in fit. Then there is, we know that there is a sum of wrestler that is a wrestler, and then there is a typical sum of wrestler which is not in fit according to some definition of being in fit or not, like, well, I don't know, it can be the ratio between weights and height, something like that. Okay. Then the first type of reasoning that we may have in this framework is this one. So the system is able to infer in the T box, which is the part of the knowledge graph dealing with the classes. We can infer that the typical wrestler is not a sum of wrestler. We can infer that the typical of wrestler that has long hair is in fit, because this is an irrelevant property. And we can infer that the typical wrestler, which is also a sum of wrestler, is someone which is not in fit. So this is from the T-box reasoning. But if we want to reason on the instances, okay, on the data points, well, given this example, which is the same that I showed you before, we can say that if we have this guy here, which is Roman, that is a wrestler and is also a sum of wrestler, we can conclude that Roman is not in fit. But if we have, for example, this other instance here that is also Roman, we can expect the conclusion that Roman is, on the other hand, in fit. So this is, let's say, the kind of reasoning that the first ingredient of the logic is able to provide. Okay. The other, let's say, important aspect concerns this notion of distributed semantics. So what does it mean? It means that we are not just able to have expressions like this one, but we can also attach probabilities to typical expressions. So we can say that we believe with a probability P that typical C, like typical, I don't know, students, are also social media users. Okay? So we can attach this kind of probabilities. And in particular, let's say we have combined this typicality-based logic with probabilities in order to, let's say, deal with the problem of the generation of different possible scenarios in the problem of concept combination. So let's see a little bit how it works, this distributed semantics here. Imagine that we have this kind of knowledge base here, okay? This is a knowledge base with 4 axioms. So the last axiom is, let's say, a certain axiom. So we know that Kevin has an animal that is called Tom, okay? The other 3 axioms are probabilistic axioms, okay? Expressed by using this kind of notation. So we know that there is a probability 0.3 that, let's say, who has a pet is also a natural lover. There is a probability 0.6 that cats are pets. There is a probability 0.9 that Tom is a cat. What happens here with this distributed semantics is that we can generate all the possible 2 to the power of n scenarios. So we can generate all the 8 possible words in which we can take, let's say, this kind of probabilistic axiom or its complement. So it means that in these first scenarios, all these elements are assumed to be false. So it means that I take the complement if I want to calculate the probability of this scenario, right? Or we can take, for example, we can calculate what is called the probability of a query. So we can say, what happens if I want to know if Kevin is a natural lover? Well, if we consider this last word, I can say that the probability of this last word is given by the multiplication of the probabilities associated to every and each, let's say, uncertain axiom that constitute this knowledge base. So this is how it works, the semantics. And this was also included within our framework, together with this last ingredient, and then I will try to show you how all these 3 things go together for solving the problem of the pet fish, okay? And the last element that is included is this head modifier heuristics that comes directly from the field of quantitative semantics. So the idea is that when we have 2 or more elements, 2 or more, let's say, noun-noun combination to do, there is always a head, which is the stronger element of the combination. It means that we want to inherit, for example, more features from the head, and then it is possible to have 1 or more modifier, okay? So we also included these elements within our system and within our formalism, and we ended up with this kind of framework. So TCL is a framework that allows you to represent within a knowledge base both standard rigid properties, which are the ones that you can already express in ontologies, in knowledge graph. Okay, you can say that all the fishes live in the water. Okay, this is a rigid property. It is like the case of the triangles. Okay, it is let's say specify necessary or sufficient condition for defining a class. Then you additionally can also specify typical features assigned to a category, included with, let's say, its probabilistic values. So you can, it is possible to represent uncertain information within this kind of extended description logics. And this is actually what you can do with the first component, with the ALC plus T logic, okay? The second component that we included, the distributed semantics, allows you to reason on all the possible probabilistic scenarios that can come up based on the combination of the different features of the two or more concepts that you want to combine. And the important thing is that you can rank these probabilities, okay? You can say, okay, and then I will show you an example based on the pet fish. You can have a rank, probabilistic rank of all the different possible scenarios that comes up with the combination of, for example, the concept of fish with the concept of pet. And finally, it is possible by using the cognitive heuristics based on head and modifier. Okay, it is possible to select the kind of probabilistic scenarios which allows us to solve the pet fish problem. So we have shown in some publications how in this way we are able to obtain the very same kind of conceptual combination that are known in the literature of cognitive science based on this kind of, let's say, problem. So we are actually able to solve this pet fish problem. Okay, so this is just to give you an, let's say, an overview idea of how these three things go together. But again, let's return a little bit to our pet fish. Okay, okay, let's consider this first property. This first property say that, well, all the fishes live in the water, and this is, let's say, a rigid property. So this is something that can be already asserted in standard knowledge graph. Then we have all these other probabilistic axioms which are associated either to the concept of a pet, or better to a typical pet, or to the concept of a fish, or better to a typical fish. Okay? So we may have different scenarios of this combination. So in the combination, it is possible to have a combination when some features are inherited and not others. Okay? So what we have, what the probabilistic semantics gave us, is the possibility of calculate, okay, the probabilities of every scenario. Like, let's consider a little bit this case. In this case, we have these first two, let's say, axioms which have not been taken. So instead of taking the probability of 0.9, we take the complement. Okay, so we take 1 minus 0.9, which is multiplied for the probability of the complement of these other axioms, which is not taken, so 1 minus 0.8, multiplied for the actual probabilities of these axioms that is taken here. Okay, in this way, it is possible to calculate the probabilities of all the different kind of, let's say, compositional scenarios. And of course, we can just rank these probabilities. Okay? Finally, let's say, another element that is required in order to deal with the problem of pet fish-like, let's say, combination is the fact that the inherited, the selected scenarios must be consistent, must be non-trivial, and of course must respect these head modifier heuristics that I mentioned. So the head must be the winning, let's say, element of the combination. So let's see a little bit all these cases, which they belong to different selection criteria. So this kind of scenario, okay, is a scenario which is not considered. It is not considered because, for example, here we have a contradiction between the fact that a typical pet must be affectionate, and then we have, on the other hand, the information that the typical fish must be not affectionate. So all the scenarios have inheriting in a joint way these two features are discarded. Or all the scenarios that, let's say, all inherit, for example, information coming just from, or mainly from the head are also discarded. And finally, all the scenarios where the modifier is preferred with respect to the head are also discarded, okay? Like in this case. So in this way, we were actually able to build a bunch of applications based on the fact that we were able to have these forms of human-like, okay, typicality-based common sense concept combination. And the applications range from cognitive modeling, and I think in a couple of days I will show you some application of this. I just wanted to give you the idea here of the overall framework. We used some application in the context of computational creativity for characters generation, for example, in cartoons, okay, this kind of creative industry, or for the recommendation of novel hybrid genres. This was a project done in combination with RAI. And in the next talk, I will mainly focus on the kind of work that is related to, let's say, cognitive system, cognitive robotics. So I will show you how, a couple of examples of how this framework has been used in order to, as the title of, let's say, the overall session suggests, how to generate novel knowledge in order to solve, for example, robotic problems or agent problems. So I will end up here, and I'm open for questions.
Thanks for the talk. That was really great. That looks like Markov logic networks, but for description logic. Is that right?
Yeah, sort of.
Yeah, so Markov logic networks come at a high price, and it looks like you also pay the price of the power set. Is that true?
Okay, this is a very good question. Yeah, we pay the price. We pay the price because the complexity of the formalism is exponential time complete. But this is the same complexity of standard description logics. So this means that in concrete applications, you can, for example, find standard description logics and ontologies and knowledge graph are used also in industry. So it is possible to find ways to actually, let's say, reduce in practical application the tractability of this system. Like, for example, we are working on that. I didn't show you. We are working on the fact of not generating all the possible, let's say, scenarios. So do not calculate the entire tables of probabilities, okay, for the possible scenarios. There are ways we are trying to deal with that. But what we managed is to do was not to increase the complexity of standard description logics. But in this case, so it is still high, it is still, let's say, exponential, but we didn't increase the complexity.
Okay, yeah, thank you. And how do you learn that? So normally Markov logic networks are learned via maximum likelihood, but you didn't introduce a partition function here or a likelihood function, so...
Yeah, so I didn't talk about the learning part of these probabilities, because we actually focused on building this mainly knowledge representation framework. From our point of view, the probabilities can be learned in many different ways. So it is important for it was important for us to, let's say, combine these aspects in order to have these, let's say, data-driven, let's say, number association associated to the axioms. It can be learned in different ways. So by using different kinds of machine learning algorithms. So for example, we mainly dealt with text-based, textual-based input, and in this case we used a bunch of, let's say, library in order to obtain the probabilities, for example, of concurrencies between the facts that were extracted in order to form the knowledge base. But we are agnostic with respect to the learning mechanism that can be used to feed the reasoning part.
Okay, and what about the axioms? How are they learned? Because that's another exponential hard problem.
What? About the
axioms, so the formulas itself. Because what you do in Markov logic networks is you just write them down and then fit the probabilities, but finding good formulas is a really hard problem. So how do you do that in?
Up to now, in these, let's say, first cases, the formulas were already there,
okay, good.
On the table. But in other application, we had to, for example, here we had to extract the relevant, let's say, formulas of our typicality-based knowledge base. And okay, I don't want to say something that I will also say in the next lesson, but in general, the idea is that, for example, by using, at least by using textual input, like in this case we had the entire database of the RAI, which is the main public broadcasting company in Italy, we were able to extract the main typical features of the different genres, but by just doing, let's say, using standard information extraction techniques based on, for example, what is typically, how much the word, I don't know, suicide co-core in the genre which is labeled as horror, or in the genre labeled, I don't know, Western or whatever, okay? So by just using these standard libraries, we were able to extract what, in our cases, we considered typicality-based formula. As I mentioned, the typicality comes from the context. Mm-hmm. So how good is a typical representation depends on the kind of context that you have. We didn't have a measure, a benchmark for say this is a good representation, mm-hmm. a good typical representation. Because a typical representation is always something that comes out from, let's say, the statistics. Also, the prototypes that we build comes out from the exposure that we have to particular type of birds, particular type of, I don't know, other forms of categories, particular way of doing things, and so on and so forth.
Okay, thanks.
So when you were talking about typicality, I was thinking about whether actually the domains we are defining ontologies with are not the wrong approach, right? So we are defining birds as things that can fly, but we know that not all things can fly, right? Kind of an alternative could be that we are building up ontologies on the basis that would somebody else that I ask now classify that as a bird and why, right? So then we are not actually defining the ontologies based on the properties of things, but rather kind of see ontologies as a way of exchanging information efficiently in a community, right? And see it, build it up as a resource infrastructure.
So you are right. So if I understood correctly your comment, it is like the way in which we define ontology is always, for example, subject-centered, while the way in which perceive, okay, is event-centered, for example. So it is possible, but on the other hand, it is easier for us to communicate this issue when we change the perspective. So when we pass from the, let's say, an event-centered ontology to a subject-centered view, let's say, of the same knowledge. So they are different views on the same kind of knowledge that we have. It is possible that we have different, let's say, we may have also in a system different levels which, let's say, explode these different views that we may have. Because, of course, the event-centered kind of representation is much more connected to the lower, to the perceptual part, right? So to the data that you come, that you receive, for example, from sensor, from I don't know, all these other issues that we have that we use in robotics. So I agree. So probably I'm not sure this is the wrong way, but we are for sure missing the way down. So which is probably the middleware, the kind of middle type of representation that we need to connect the perceptual part with these forms of, let's say, higher level reasoning and representation.
Okay, give me a second.
Thank you so much, since the book is already here. So, you not only talked about having this fuzzy logic-esque representation of recombining the facts into probabilities of how likely two concepts are combined together, like that shark with horse legs is, well, it may exist somewhere. Combined with natural language processing, or finding out how to segment natural language. So to hook onto Michael's idea and have people discuss about concepts and contexts, would it maybe be possible to traverse through forums where they talk about these things and try to find out, based on their context, of course, what they think about certain subjects and how to represent them? If we probably can assign some facts or probable facts about them, what are your thoughts about that?
Yeah, I mean, let's say in principle, I agree with your points. That there is also a lot of work done in context-based logic, contextual-based formalism, in, let's say, classical AI, classical symbolic AI tradition. So for sure, I mean, your suggestion can be taken into account. So I will not be, let's say, scandalized by having this kind of, let's say, hybridization. But for what concern, one point that is important here is that this is a kind of logic, so these kind of things cannot be done by using standard fuzzy logic. Mm-hmm. So this is the first, let's say, part of the comments that you made. It cannot be done because you encounter this kind of problems when you deal with fuzzy logic. Let me see if I have, yeah, probably here. So when you use a fuzzy logic, there are of course different kinds of logic. So let's assume that you want to, let's say, represent the information about this polka dot zebra, okay? So it is a zebra that has also this kind of polka dot things. You can say that, well, this zebra that we can call Pina, okay, is a polka dot zebra with a probability of 0.9. But we can say that this is an atypical zebra, right? So it's quite atypical as a zebra because zebras have stripes. So we can say that Pina is a zebra with a probability 0.2. So the problem here is that if we use, let's say the form of most widespread fuzzy logics, including Gödel logics and so on and so forth, the value of a conjunction is calculated as the minimum of the values of its conjuncts. Okay, so fuzzy logic is not good for dealing with the problem of common sense. I mean, I didn't go into the details of this, but this was one of the first approaches that was tried in order to solve this kind of typicality-based concept combination, but they didn't were able to manage this kind of stuff. So that's why this is what the TCL frameworks, let's say, adds. It provides a symbolic, grounded framework that is also able to, let's say, deal with the data, of course, with the values, with the probabilities coming from the actual external world. What is this world? This world can be, let's say, so the data can come from different sources, from text, from vision systems, from sensors, and whatever. So, as I mentioned, we are agnostic with respect to that part because we try to develop this, let's say, knowledge representation and reasoning system mainly. But now we are also dealing with, let's say, the other side of the coin.
Okay, thank you.
Okay, thank you. One short last question, or is there one? Okay. Usually, okay.
Were you able to generate a dogfish that is accurate?
Sorry?
Were you able to generate a dogfish that is accurate? Because dogfish is an actual animal and a mixture of dog and fish.
We're able to generate the talk.
A dogfish.
A dogfish? Yeah, I can, and I can show you. I mean, I can eventually show what is the result. So the point is that you can combine. So you can deal also with potentially inconsistent combinations. So the system using this framework, for example, for computational creativity, are able to let's say identify which is the kind of, let's say, head modifier, let's say, combination. That means that in this kind of strange animal, okay, which could be also the dogfish and whatever, you may have a shark which has also, let's say, the feature of having 4 legs and of not living in the water. So this means here that system identified that the horse, it tried all the possible, let's say, combination in terms of what is the head and what is the modifier, but it ended up by choosing the concept of horse as the head of the combination. So it means that most of the features which are inherited in this kind of strange combination are the ones coming from the head, but there are also some features coming from, in this case, from the shark, but it can be also a dog, it can be whatever, okay?
Okay, thanks.
Thank you.
That's it. I think we need a break, some refreshing. Okay, thank you very
Thank
much.
you.
This
See
was
you next day.